9.
All right. Well, actually, you know what? Point out that kind of stuff over the weekend. Send that to me Sunday afternoon, along with all the other changes you want me to make,
Yeah.
and I'll do that. Because if we get doing that right now, we'll get doing that instead of machine learning,
Okay.
and we'll burn it the rest of the time we have today. So, yeah. So I realized that I have changed the dates for several of years, Gaston, but that's because I'm trying to eliminate as much as possible any gaps that you have in your employment.
Yeah, that's good. This time it didn't
Because
need
Jeevan
that.
also, at this place where they hired him,
Yeah.
they asked him about that. He fortunately had a good answer because he had a gap of something like 7 years between when he got his bachelor's and when he got his master's. And then he's worked consistently since he got his master's, but they were like, so what were you doing for like 6 years between like when you got your bachelor's and when you got your master's? And he was able to tell them like, oh yeah, I was teaching at the university and participating in research, you know, I was doing this, that kind of stuff, and they were kind of like, oh, okay, you know, like, so lucky for him, they totally bought it, and they were fine with all that.
If they understood what he was saying.
But,
Jeremy, something else.
what's up?
Oh. Sorry, I forgot.
That's right.
Can we do the master at the same time that we are in our CV present that we worked at the same time?
In fact,
Because I want to
unless there's some huge cultural difference between here and the US, that's actually incredibly common.
because I want to connect actually my education with my job, my relevant job.
Uh-huh.
So I want to ask about that.
Yeah, so it's very common to like wrap up a bachelor's degree and then go into industry,
Yeah.
but be working on a master's degree at the same time.
Yeah.
So very, very common. In fact, a lot of people told me, because I was actually planning on just immediately going to graduate school after I finished my undergrad.
Yep.
And the whole reason I ended up not, and the reason why I went and got a job, is, well, partly because my wife was ready for me to start making money and have me not be a student anymore. But also, a lot of people that I really respected, and that, you know, were really successful and had gotten to really good places in life, all pretty much gave me the same advice independently, and that was, if you just go to school, then it just, the longer you do that, the more and more disconnected what you're learning actually is from what you're really going to end up doing once you actually do join the workforce. So you're better off getting a bachelor's degree so that you can get a job, go get a job and actually work for a little while and decide what you really like and what you really want to do, and let that inform what kind of graduate track you would get on. Because if you just go straight from a bachelor's degree to a master's degree, then hopefully you really like doing whatever you got your master's degree to do. But you might actually get into the workforce and realize that you hate doing it, or that you're actually really good at some specific thing, and that rather than the master's degree you would have gotten, there's this other master's degree that's actually more useful, and you can get that one instead because you know that now. But yeah, so in the US, very, very common to wrap up a bachelor's degree, start working so that you start having some income, and then while you're working, you finish up a master's degree.
Okay. And then here it's easier because it's just 1 year.
In the US, it's 2 years, but that's even if you go full time. If you're working, a lot of people don't go full time, they go a little bit less than full time. And they take classes at night and stuff like that. And so some people, it takes them maybe 3, sometimes 4 years to finish a master's degree because they're doing it while they work.
Yeah, part-time.
So,
But here it can be done.
all right. So, we have a lot that I want to teach you guys, and I don't have a lot of time to teach you. Because I was actually hoping that we could be quicker than we normally are with our presentations, and we actually burned up the entire morning doing presentations. But I want to teach you guys enough that you can actually go home and start working on artificial neural networks, right? Because some of you are actually there. You're actually to the point where you would do that with your model.
We
So-
can do some extra class after.
I can't. I actually have to do a tech test for Mabu today, and I still have Jeevan's thing to do since he's clearly not going to do goddamn anything. So let's do this. So the only thing that you really do to go from what you know how to do, which is logistic regression, multinomial logistic regression, is you just add another layer. So we'll say that the greens are your inputs, right? So here are your input nodes, or these are the blues, sorry, since this is the marker I ended up with in my hand. Right, so this will be x0, x1, x2, x3, x4, right? And for multinomial logistic regression, you would then have these outputs here, and we call these like P, right? So P1 up to PK, right? I'm going to label these a little differently now. I'm just going to call these Z. So we have a Z0, Z1, Z2, Z3, and Z4. And we don't necessarily have to have the same number as we have, you know, outputs. Right, so this would be what a multinomial logistic regression would look like, right? So we have everything networked to everything else between layers, right? So we've got a thing like this. Every input is connected to everything in the next layer. And I'm not doing this on purpose, but let's even say that the different thicknesses are maybe like different weight values. So if it's thinner, it has like a smaller weight, right? So all of these connections are weighted differently. Right? So here's what a multinomial logistic regression looks like. For an artificial neural network, we're now just going to say that there's this layer here in the middle, and that our outputs are now over here. Right? So now this can be, for the sake of, you know, we're going to say that this is like for classifications for the sake of being able to talk about it. Right, this is our p hat 1, p hat 2, p hat 3, p hat 4. Right, and the numbers here actually correspond to the class. And so now we just treat the jump from this layer to this layer like this is also a multinomial logistic regression. We connect everything in this layer to everything in the next layer. And we, yeah. And now we would call this our hidden layer. Right, so then this is our input layer, our output layer. And then the thing in the middle is the hidden layer. And that's it, you have a neural network. It's not quite that easy, there's a little more to it than that. But this is the gist, right? This is the main idea. And when you have a deep network, or when people refer to deep learning, there's nothing really magical about that. It's just the case that you have more than one hidden layer, right? So you would have, we start to label them with these kind of superscripts that have parentheses around them so that we know that we're not like raising something to a power, right? So we'd have our first hidden layer, we'd have our second hidden layer, and so on. And so a deep network basically is some network that has more than one hidden layer. That's all there is to it. That's all there is to deep learning, just about.
Can Jeremy, where you are connecting from the hidden layer to the second or the output layer, is the actual output of your first multinomial logistic regression?
Yes, except, so say we're talking about like your e-commerce data, right? So your user actions, what's that going to be? That's going to be this. That's going to be the green output layer,
Okay.
right? The hidden layer doesn't necessarily have to represent something. What?
It's not an input layer.
Your user actions?
No,
Your target?
Is
Ah,
our
exactly. Yeah.
Yeah,
That's
that's
our-
the output layer.
that's
Yeah,
how-
yeah.
So the things that you'd use, right, like what time of day it was, are they a mobile visitor, are they a repeat visitor, whatever.
that's
These are all, this is your blue stuff, right? This is your inputs,
Yeah.
right? And then you have the actual user actions, which is your output. So still, it's kind of the same, or well, still is the same as the multinomial logistic regression you guys have been building, where you still have the same inputs and you still have the same outputs, right? Those still mean the same thing. You just now have this other layer in the middle, right? What is it? What is it exactly? What does it represent? Like, hard to say. That's why we call this a black box algorithm, because kind of the whole decision path is pretty hidden to us, right? We don't really know what it is. And we know what our features are here at this layer, right? We know what our input features are here, but then they get encoded into these things, which are then kind of the input features for this layer here. But like, what do these features mean at this point?
And how many
Don't
of them? How many of them do you engineer them, or how many of them do you use?
You don't really engineer them. That's kind of the other thing, is that the neural network, in a way, some people think of it this way, and it's not incorrect, is that the neural network is kind of engineering its own features within the hidden layer. Again, it's not totally clear to us what these are, or if there's any kind of real interpretation of these features, but nevertheless, that's what they are. So that's why it's very hard for us to interpret artificial neural network models.
So
Right.
So you don't choose how many of those seeds.
No, you do.
You do. Ah.
And this is just kind of another hyperparameter. So in a way, some people are, I've heard people say this and it's incorrect, where they're like, oh yeah, so that's the great thing about neural networks is they engineer their own features, right? And they say that almost as if it's like easier, right? Like, oh, you got this thing that engineers its own features. Like, oh shit, it's easy, right? Well, sort of, except we still have the same hyperparameters that we would always have, right? Like for regularization, right? There's like lambda 1, lambda 2, and we need to find like ideal values of this. We still need to figure out the best learning rate. We still need to figure out the number of training epochs. Like there are all these things we have to figure out that we still had to, or that we had to figure out before to make our model work. We still have to figure those values out to make this model work. In addition to that, though, you kind of have these other layers, like, you know, I'll just kind of denote it with L. One is the number of layers that you're actually going to have in your network. That's one hyperparameter. And then for each hidden layer that you have, so you don't really control how many inputs you have or how many outputs you have. Those are kind of determined by your data and by just what your target is. But here, I don't know, let's pick a letter for this. So Q, let's say, is the number of nodes or the number of, so some people say nodes, some people say units, some people say neurons, right? The number of things in your hidden layer. This is also a hyperparameter that you need to figure out.
You say somewhere like this hidden layers, they are actually an activation kind of functions.
Yep. So that is the thing I've mentioned before. And that's another thing that we have to figure out as well. So here you're actually applying an activation function as well. And the two activation functions that we've seen up till now are the sigmoid function, which you certainly can use here. Lots of people do. Lots of models still use the sigmoid as an activation function. You can use the softmax, which if you're doing classification should always be the activation at your output layer. You still can use softmax though on your hidden layers, perfectly fine. But there are still other options that you have. So another one is tanh, or the hyperbolic tangent function. I've seen also the arctan function, and there's also rectified linear unit, or ReLU, so that we actually now have kind of this whole slew of activation functions that we can choose to use at our hidden layer.
Jeremy,
And that's kind of another thing you have to figure out, yes.
still I don't understand why if we can go from the input layer to the output layer to add the hidden layer.
Why what?
Why if we can go from the input layer to the output layer to add this hidden layer?
Why would we add it?
Yeah.
So this actually,
What it helps, what it improve our model, what
so we'll have weights, right? So we'll have now a weight matrix 1, W1, that goes into our first hidden layer. And so this, if we have D features, and this is Q elements in our hidden layer, then now we actually have this weight matrix, which is D by Q.
Yeah.
Now, we also have another second set of weights,
2 by M.
which has to be Q by K actually, so
Okay.
K is the number of classes that we actually have.
Okay.
And we also have some nonlinear activation function that's being applied here at this hidden layer, right? So this actually greatly increases the complexity of our model, which greatly enhances, expands the types of hypotheses it can be fitted to. So before, our model was linear. Our model could only define linear decision boundaries unless we actually specifically engineered nonlinear features, right? We still could engineer nonlinear features, but whether we do that or not, our model is actually capable of finding and conforming to nonlinear decision boundaries because we now have a set of weights, a nonlinear decision, or a nonlinear activation function, and then another set of weights on that output that comes out of that the model can use to conform to this decision boundary.
Jeremy, and the hyperparameters that we already know, like lambda, epoch, eta, all that,
Mhm.
where are they living in that circuit? Are they going to be activated after the hidden layer towards the output
No,
layer?
they live where they've always lived. They live in the objective function as you're training your model.
Okay.
They live in the gradient as you're doing gradient descent. Although this brings us to kind of an interesting thing that we need to get to. We'll need to address some of these other things first. But now, we can't just simply do gradient descent. Gradient descent now has to be handled a little bit differently. And so for artificial neural networks, we actually call this back propagation. The reason we have to call this back propagation is because we're going to train our model by comparing our outputs to our targets, right?
Mm-hmm.
And so you perform gradient descent and that adjusts your weights, right? But if we're comparing the outputs here to our target, we're going to figure out that we need to make adjustments to these weights, right? But then that just adjusts things from this layer to this layer. However, these adjustments that we make actually have to still propagate back to these weights as well, and the adjustments that we make to these weights actually depend on the adjustments we've made to these weights. And so in a way, these adjustments actually propagate back through the network.
See.
So is another way of saying, like we said in linear regression, like cost functions kind of thing, error.
Yeah.
Yeah.
In fact, you don't even need a new error function or a new objective function or cost function for this. So if we're doing classification, we still use our cross entropy objective function. Right? This is still the objective function you use if you're doing classification. If you're doing regression, we still train this model with the same ordinary least squares regression. So we don't even need to introduce or derive or whatever new objective functions to implement this model. This uses the same objective functions that linear regression and logistic regression have always used. And it also means that we regularize them in exactly the same way as well.
And in which layer will the regularization happen? Between the hidden and the output, or between the?
Both. It happens at all layers. I shouldn't even say both because that only applies to this single hidden layer case. It happens at all layers.
Okay.
In which case we say that they add a bias on that start like on the vector 0 or
In which case would we say it's biased?
yeah, add a bias on
In all the same cases,
oh
right? So if you know, run your diagnostics and the diagnostics look the way that I said they would look for linear regression or logistic regression, to indicate that whether your model is high bias or high variance, still means the same thing here, right? Those ideas were completely general to all supervised learning. Okay? So, which this is. So this is still a supervised learning case, which means that we still start out with a bunch of training examples that are of the form xi, yi, right? Where we have n of these, and x is in d dimensions, and y is potentially in k dimensions, right? Exactly the same. So of the whole setup, the whole idea, everything is exactly the same as everything we've seen so far, right?
Mm-hmm.
And the only thing we're doing now is we're performing one logistic regression where we're kind of inventing this other layer, right? We're deciding, okay, so there are Q outputs here, and I'm going to define a logistic regression that goes from my input layer to this layer that I've made up, and then I'm going to define a second logistic regression that goes from this layer that I've made up to the output layer.
And this new hidden layer always has the purpose to decrease the bias and increase the beta variance, like.
So going from what you had before, where you just had, logistic regression, multinomial logistic regression,
Yeah.
to this, always increases the variance of your model.
Mm.
You have more weights, you have more moving parts, you have a nonlinear piece here in the middle. So you're definitely increasing the complexity and therefore increasing the variance of your model, right?
Mm.
And in general, we'll say that variance increases directly with the number of layers. So the more layers you have, the more variance. Yes?
Can you please give, in our database, for example, e-commerce, an example for the artificial neural network? How will fit?
How you will fit it?
Yeah.
There's still quite a bit of math that we have to go through to talk about how you fit it.
Okay.
So I'm just trying to give you guys this general intuitive idea of what it is we're doing.
Can I ask you one more question?
Yeah.
So if you see that in the diagnostic there's something wrong, okay, do you also need to do something to your hidden layer if you see that as part of your diagnostics or something?
Yeah, so one of the things I would actually mess with in my diagnostics would be Q.
Yeah.
The smaller Q is, the lower my variance is going to be. The higher Q is, the higher my variance is going to be. So you could even bring Q all the way down to 1, right? You literally could have like 1 unit in your hidden layer.
what we just said, like it
So-
generated itself. How could we make it like a 1 or 2?
What do you mean?
Because you're saying that the hidden layers, what people say that they being generated themselves or create themselves, not really. But then how can we make that like to 3 units or
You can make them
neurons?
any number of units you want. You write the code. You build the model. You decide all that stuff. So yeah, I certainly might run a diagnostic where, this is Q, for even just this layer, right? Before I mess with the number of layers, right? I might plot my training and validation errors against the number of units I even have in my hidden layer.
And how is this different to engineering polynomials or engineering features? Because that will also
You're just giving the
expand-
model a way to kind of engineer its own features.
Oh, these are engineering
Yep.
features. Right.
But the model will never engineer more than Q features.
Right.
You'll be amazed at the complexity that the model is actually able to come up with even a small number of neurons, right? So this is kind of why this would be preferable to engineering a bunch of polynomial features, is because you actually can get some pretty incredible results with even just like 5 or 6 nodes in a hidden layer. Because of the nonlinearity of the activation function, and because you actually now have 2 weights that 2 weight sets that exist between your input and your output, this actually enhances the complexity as far as like what your model is able to fit to quite a lot, without really increasing the complexity in terms of like the practical exercise of actually fitting your model. Whereas, as we were discussing before we left for lunch, fitting or engineering a bunch of polynomial features increases the complexity of your model insanely fast, right? So like when you were talking about your model, you had 9 weights, right? Like 9 features. You want to start inserting or making polynomial functions of your 9 features, your 9 variables. That's going to get insane, like really, really fast.
Yeah.
Right? Because that means you're going to immediately, even if you just had all of your pure terms, you immediately go up from 9 to 18 features, because you have all your features and all your features squared. If you include your cross terms, then you have to have like x1, x2, x1, x3, x1, x4, x1, x5, and so on. But then you have, you don't have x2, x1 because that's the same as x1, x2, right? But you do have,
X squared.
x,
X1
x2,
squared.
x3, x2, x4, x2, x5, and so on, and then x3, x4, x3, x6, x3, x5, all that stuff. So in general, the number of cross terms you would have if you have, say, d features would be 1/2 d squared.
Yeah.
So if you have 9, if you have 9 features, then if you're going to do all of your quadratic terms, then so 9 squared would be 81, but then half that. So that would be, so it's hard to know exactly what that would be in half.
Yeah.
This is kind of a general
40,
formula.
40.5.
Yeah, so, but you'd have like 40, 41 features,
Yeah.
something like that you engineered just with your next step up, going from linear to quadratic.
Yeah.
You've gone from 9 features to 40, right?
Yeah.
So that's a pretty
Massive.
sizable leap in complexity, right?
Yeah.
Which also, because of just kind of like programmatically what it would mean to engineer all those features, just means that the exercise of implementing that is enormous, right? It's a huge headache. On the other hand, I think you would find that your model is actually able to match or even surpass that kind of complexity if you had a neural network, and it's not nearly so difficult to actually implement, right? And you can seriously have like 5 or 6 nodes in your hidden layer.
And when you say that if this hidden layer is like a black box, it's because we don't really know what this hidden layer is doing to the weights that's passing.
But yeah, there's not really like a practical interpretation or like a real interpretation of like what's coming out of the hidden layer and going into the output layer, right? Because really, your output layer kind of doesn't even see what's anything that's like further back than the hidden layer that's before it, right? So the features really that your model is using to make its final output is like whatever these are. But like, what are these? Like, I don't know. So kind of beyond your input layer, it's really, really tough to say like to like interpret anything about what the model's doing.
But
Right.
these are features that could potentially be, for example, I don't know, x to the power of something, and then with the x to the power of 2 with the
Not
x.
really, because we're not really applying those
Oh,
sort
yeah.
of functions to them.
Yeah.
And really, for the most part, you've got sigmoid, hyperbolic tangent, and arctangent that all have sort of this like logistic S-shaped
Awesome.
curve to them. Softmax in general doesn't quite look like that, although it's not really far off of that. It mostly just kind of looks like that part of it. And then ReLU, or rectified linear unit, is actually, I don't know, it looks like a bunch of broken sticks actually, is what it looks like. But we'll get into what that is.
So Jeremy,
So, yes.
no, please.
So what we're going to need to do in order to figure out how to train this model is we're going to have to first kind of cover these activation functions we might use and what their derivatives look like, both on paper and in code. And then once we've actually figured out how we might take the derivative of these activation functions, because that will matter for this layer, we have to figure out what does our gradient look like with respect to this set of weights, and what does our gradient look like with respect to this set of weights, so that we know how to train both layers of our model.
We started with
What does
5 input. We ended up with 4 output.
This is not a general. That's just however many circles I felt like drawing. That's all that is. So I'm just trying to show you the general structure. This isn't like every neural network ever looks just like this. Okay. So like if you were to deal with like the MNIST data set, which is a bunch of images, like scanned images of hand-drawn digits that are 28 pixels on a side, I think, something like that, then actually each observation is going to be your pixel brightnesses for the scan. So let's kind of run that through a calculator real quick. So if you have each image is 28 by 28 pixels, and then each feature is literally the brightness of a pixel, then your feature space is 784 dimensions, which means that you'd have 784 nodes in your input layer. So, but I'm not going to sit here all day and draw 784 circles just to show you like what, you know. So that's why it looks like that.
Jeremy,
Yes.
so actually everything is in the hidden layer actually is random.
It's not random. You actually
How
are,
it generated?
when you generate it to start out, you are going to randomly initialize this set of weights and this set of weights. Okay? In that sense, I suppose what comes out of your hidden layer in the beginning is random because it's dependent upon this and is therefore, you know, kind of random. But it gets trained about as quickly as anything else when when we've trained models before. Okay? So, all right, so that's 2:30. That's supposed to be our time, but we haven't really gotten into anything because I'm answering like a bunch of random questions. So, would you like me to explain to you how to
Yes.
train this model?
Yeah.
Okay, so we start with either of these objective functions, depending on whether we're doing classification or regression. Okay? So since you guys are currently working on a classification problem, let's look at how this is going to go if you're doing classification. I'll later show you actually that it doesn't matter. It looks the same either way. Shouldn't be surprising actually because our gradients for both linear and logistic regression ended up looking identical. So that shouldn't come as a huge shock to you that that's coming up, but that is coming up. Okay. First I'm going to need to actually explain to you guys another method, another more general method of derivatives. Maybe I don't have time to do this today. I'm realizing now how much stuff we have to cover. Okay. So there's this thing that we call a total derivative. I'll give you guys until 3. So.
What do you use?
Huh? I'll give you guys until 3. So I have 30 minutes to get through this. So here's the idea behind the total derivative. Let's say that we have a function f, and f is a function of both x and y. Okay? Now let's say that in turn, x is some function of some other auxiliary parameter t, and so is y. Right? So really, f is kind of a function of t, but indirectly. So in this case, we actually might want to figure out what's the derivative of f with respect to t.
That's just like the chain rule, isn't it?
It is, but we just need another little extra bit. Because t changes, right? But changes in t will bring about both changes in x and y, which will both bring about changes in f. So it's not quite so simple as the chain rule. So if we want to find just the changes in f that are brought about as t changes through x, then we actually do use the chain rule there, right? So we do di f by di x, and then times dx by dt. So this gives us the change that results in f through x as t changes. However, this isn't all a change. So it also happens that we see changes in f through y when t changes, and so we have to add up basically all of the different changes that t brings about through all of the different direct variables of x. Does that make sense?
Yeah.
So more generally, this is kind of this nice simple case, but more generally, f could be a function of k different x's, right? So we'll go k1, k2, and so on up to, or x1, x2, up to xk, right? And then each x may itself be a function of, you know, a bunch of different variables, right? So okay, so in general, this is what we could be looking at. So the derivative of f with respect to a particular t is the sum over all the k's little k. So in general, our total derivative looks like that. Does that make sense?
Yeah.
So it just means that we have to use the chain rule to take the partial derivative of f with respect to x1, and then the derivative of x1 with respect to the particular t, and then the partial derivative of f with respect to x2 times the derivative of x2 with respect to t sub I, and so on, and do all of that, and then add up all those derivatives. Take the sum of all those derivatives to get that total derivative of f with respect to t sub I. Okay? Not too difficult. Just a little tiny extension beyond what we've already seen. So bear that in mind. So let's get to it. So we have that j equals negative 1 over n times the sum as I goes from 1 to n. The sum as k goes from 1 to k, big K, y sub I ln p hat sub I. Okay? So,
This for classification, right?
let's first, I guess, look at some of the different derivatives. Let's table this for just a second. So, hyperbolic tangent, pretty common one. I actually use it quite a lot. That's not for me. So hyperbolic tangent is defined in this way. So it's, we'll say hyperbolic tangent of x equals e to the x minus e to the negative x over e to the x plus e to the negative x. Okay, that's how this function is defined. So this is actually the exact same shape as the sigmoid function. It's actually just stretched both horizontally and vertically. So instead of ranging from 0 to 1, it ranges from -1 to 1. So I actually really like this, especially if I'm doing, so I find that I do this a lot, but I'll build a neural network that actually has 2 hidden layers, right? So we'll have like my input layer, and then we have, 2 hidden layers, and then my output layer, right? I actually quite often use the configuration. So I've got softmax here, but I'll use sigmoid here, and I'll use hyperbolic tangent here as my activation function. The reason why is because the sigmoid function actually really only kind of separates things between like whether they're like negative or positive, right? So if you were to just do like sigmoid into softmax, that actually can work, but you actually would need to make more adjustments to your weights before your model is trained. But the fact that the hyperbolic tangent already spreads things out over a range from -1 to 1 already makes them so that they're kind of in that ideal spot where sigmoid can kind of do what it's going to do, right? So for that reason, I actually like hyperbolic tangent quite a lot, and I like that configuration where I actually will feed the hyperbolic tangent into the sigmoid and then feed that from the output layer. So that's why we like that.
Just give me a second.
Oh, okay. But if we're going to use this, if we're actually going to be able to train a model that uses this activation function, then we need to know what the derivative is.
Okay.
So we're going to quick find the derivative, and then kind of for the interest of time, this will be the only one that I show you the derivative of today, just so that we can kind of get into building a model.
If your purpose is that you want to get zeros and ones or something in between for the sigmoid function, would you use like sin function or cosine or any of that?
No.
No?
No, I wouldn't. There are cases where you might, but they're the kinds of applications where you've shown that they, or where people have shown that they might be useful, or kind of niche. So, whereas this actually works very generally. Okay, so let's take the derivative of this guy. real quick. So I'm just going to call this y so that it's easier to write down. So we're going to have to use our quotient rule. So we have the top function and the bottom function. So we're going to have the derivative of the top function times the bottom function minus the top function times the derivative of the bottom function all over the bottom function squared. Okay? So here we go. So we have the top function, which is e to the x minus e to the negative x. The derivative of that guy is going to be e to the x, because that's the derivative there, minus the derivative of this guy, which is actually a compound function. We need the chain rule here. So that's e to the negative x times the derivative of negative x, which is just negative 1. So this actually becomes e to the x plus e to the negative x, right? That's the derivative of the top function, and then we multiply that by the bottom function. Turns out that's actually exactly what we had. So we get that squared. Okay? Then minus the top function times the derivative of the bottom function. So the top function is e to the x minus e to the negative x. Now the derivative of the bottom function is e to the x plus, we need the chain rule again for this guy. So e to the negative x times the derivative of negative x, which is negative 1. And so this turns into e to the x minus e to the negative x, which is the top function. So we get that guy squared. Okay? And then all of this over the bottom function squared. So that it looks like this. Okay? But now, you guys can see we actually could split this up. At least I hope you see. And so we would get e to the x plus e to the negative x squared over e to the x plus e to the negative x squared minus e to the x minus e to the negative x, squared over e to the x minus e to the negative x, or plus, sorry, e to the negative x squared. So it should be pretty clear then that we have this thing, which is 1. And then this thing, which is actually equal to the definition of the arctangent squared. Right? So then this just becomes 1 minus y squared. Because y is the hyperbolic tangent. Okay? So pretty easy. You guys good there?
Yeah.
Okay. So set that result aside for a minute. Let's go back to this guy. So first, in order to train our model, we need to find the derivative of j with respect to W2, which is our second set of weights. that goes from the hidden layer into the output layer. Okay? This is Q by K. So we're going to call this, so we're going to actually find what this would look like with respect to a particular weight in this matrix, a particular element. Right? So dj or dij by di W2 sub QK. Right? The QKth element in W. So we would use the chain rule as before, right? So this is equal to dij by di p hat times di p hat by di, I'm going to call this H2. I'll explain that in just a second. And then di H2 by di W QK. So what is this H2? I might be just trying to fit too much stuff in here. For how quick this lecture is going. Because normally what I would do is I would actually first show you guys the forward propagation, and we would like build in code, kind of like we did with logistic regression, an actual neural network, and we'd build the whole thing. We just wouldn't train it, but I'd show you guys like how it is that, you know, the calculations propagate forward. And then I'd teach you all this stuff, and then we'd actually train the model, and then we'd do back propagation and train it.
So why would you do this?
Because I literally have like 20 minutes to teach all this stuff to you guys. So recall that the way that logistic regression works, right, that we had sigmoid and that this was applied to some h, right, where h, this is p hat, where h
So X and
was this linear combination xw, right? So that means that now in a neural network, we have our h1, which is x times w1, right? And this goes into z1. So our hidden layer is whatever our activation function is applied to xw1. Okay? Now we have for our output layer, we would call this, so now this would be p hat, although in the case of general classification, we have k classes, right? So we have p hat. So this would now be our activation function at our output layer, which we're going to say for classification is always going to be the softmax function. Now instead of x, right, our input at this layer is z1. And then now instead of w1, we have our other set of weights, w2. And so with this being the case, we're applying some activation function to some linear combination of things. And so we would say that h2 is this other linear combination. Oops. That looks like that. Okay? So we need to find our derivative of j with respect to p hat. P hat is itself a function of h, so we need to find the derivative with respect to h. And then h is the thing that's directly a function of this W2, so then we find the derivative of h with respect to W2.
Can you give us 1 minute to write this?
Sure.
What's that S? The P hat equal S
Softmax.
softmax. Okay.
Softmax of that. So, and you'll actually see,
Wait, in the last section. Okay.
okay.
Yeah.
So you guys will actually see, if you like read white papers and research papers and all that kind of stuff on neural networks, and you look at their description of their neural network, you'll see that this is how they write them down, and moreover, this is how I'm going to have you code them up. That there's not really any one equation that you can give that describes your neural network, right? So instead, they're going to give you a series of equations. Each equation defines a layer in your network. So they'll tell you, they'll give you, you know, like this. So here's, you know, what we're doing at, you know, the first layer. Here's what we're doing at the second layer. And then here's, you know, what our output is. Like this, you know, so they'll actually just kind of describe this in terms of like a series of equations that explains. You take x, you put x in to this formula, that gives you z1. You then take z1, put that into this formula, that gives you z2. You take z2, you put that into this formula, you get p1. Because that's literally what, I mean, you're just composing a bunch of functions basically, right? I mean, you could write that all in like a single equation, right? So you could actually, where you see z2, we can just put this in there, and then substitute that in. And where we see z1, we can substitute that in and just keep doing that, but that'd just be like a beast of an equation to read, so we don't want to do that. Okay? So, in order to we're gonna have enough time to do this. This sucks. So first we have to figure out what this derivative looks like. Okay? So this thing, we've already figured out what this derivative looked like, because that was exactly the same. This is exactly the same as when we were doing logistic regression before. In fact, this just kind of is like finding the gradient for a logistic regression. Okay? We've already figured out what the derivative is with respect to this guy, because p hat is just the softmax function, right? And h is just the thing we feed into the softmax function. We've already figured that out. And then this is just a linear thing, right? So hopefully you guys, hopefully it won't be too hard for you guys to believe me when I tell you that this gradient is going to look like well, actually, no, there's just a particular K. So this is going to look like, let's see, Z1 IQ times P hat sub IK, where again, this is maybe we'll say that this is K prime to denote that it's some specific K that we mean. Right, this looks like this. And you guys already know that when we go, that this actually defines a matrix product. And so this actually literally just looks like, when we say the gradient with respect to W2 of J equals 1 over n times Z1 transpose times P hat minus Y. So that should look pretty familiar. That actually is exactly the gradient from logistic regression. It's just that now instead of X as the input, we have this hidden layer Z1.
This in K is the max, K max.
This what?
In this K, in the K,
K.
yeah,
The super stop.
This K?
yeah,
So we're looking for the QK prime element in this matrix, right?
okay, yeah.
The derivative with respect to that specific weight, right?
This is one specific, right?
Yep, it turns out that it's this, right? That it is this, so this, if you, again, figure that these things are matrices and that their rows or columns are vectors, then this actually ends up being the dot product with the qth column of Z1 and the k prime column of P hat minus Y. Which is the same as saying that for any given one of these, or that if we want to calculate this for all of these at once, this ends up being this matrix product. Right? This literally defines a matrix product.
Yeah.
Right? Because this actually by itself literally defines a dot product, but this tells us that the QK prime's element
This is specific.
is this dot product with the qth column and the k prime's column, which means that it's this. This is the matrix product that is defined by that. Okay? So we're halfway there. That's good. So this part didn't really require us to learn anything new. Right? We just have to remember that in this case, the thing that we treated as X is actually the hidden layer. And that's it. But that doesn't change anything. This still looks the same. So the only thing that's going to require us to learn anything new now is the gradient of J with respect to W1. Right? To any weight in W1. What's that going to look like? So, and it is 3 on the button. So, let's see here. All right, I'll give you guys 10 more minutes. I'll try to cover this, and then I really do have to go. Okay. So now, what we have to remember is that the changes that we're going to make, right, the gradient with respect to W1 is actually going to depend on changes that we made in W2. Right, so now we need to find the derivative of J with respect to an element in W1, and this is D by Q. Right? We have D input features and we have Q things in our input layer, or sorry, our hidden layer. This thing is d by q. So, again, j isn't directly a function of this. J is a function, though, of z1, right? And z1 is in turn a function of h1, right? The logit that goes into that layer. And then h1 is the thing that is a function of w1. Okay?
What is the last one? J.
dq. Little d, little q. So this is where we actually need the total derivatives, because actually for a given z, right, because z, if you think about it, the thing that comes out of our hidden layer, z1 is the result of us taking x, which is n by d. We're multiplying this by w1, which is d by q. So we get an n by q matrix. We apply some activation function to it, but we still end up with a d by q matrix. So this is, or with an n by q matrix. So this is n by q. Okay? So that means that we actually have q different things in this layer. But j isn't even directly a function of these q different things, right? It's a function of k different p hat values, which each one of those is a function of these q different z nodes, right? Or z units or hidden units. So this is where we actually need our total derivative method, right? So if we're going to execute this derivative here, we actually do need this thing. So I'm going to put a sub k prime here, even though this is an n by q thing, to denote that we're actually getting to that particular thing in z via the k prime thing in the output layer, right? So our kind of path to this thing, because we have all these things in the hidden layer, we have these things in the output layer. And so j is a function of any one of these, say this, through each one of these, right? Because this gets fed into this, and this, and this, and this. So j is actually a function of each of these things, and each one of these things is a function of even just this one thing, right? And we actually have q of these things, and each one of these k things is a function of each one of these q things. Okay? So we have to bear that in mind when we go to execute this derivative. So let's figure out what this would look like for just a particular k, right? Because now, so let's apply our total derivative rule. So then that means that di j by di z1, and we'll call this iq, right? So the q thing in here, or we'll even, so forget the I, forget the whole part of like that there's a
We know
that there's like that there are like different observations, right? That we have all these different examples. But according to the total derivative, because it's the case that j is a function of p hat 1 through p hat k, and each one of these is a function of this, then this ends up being the sum as little k goes from 1 to big K. Die j die p hat k times die p hat k die z sub q. Right, so this is just our total derivative rule here.
I was asking, are we not still doing the derivative with respect to w dq?
Yes, we are. But we have to use the chain rule quite a bit to get there, as you can see, right? Because in order to get to this guy, we need to get the derivative of j with respect to z1, the derivative of z1 with respect to h1, and the derivative of h1 with respect to w1, but it's not even quite that simple because the derivative of j with respect to z1 for some particular k prime. So rather than say that at this point, forget that. The derivative of j with respect to z1 period is actually equal to this. So we have to use our total derivative rule to even get that, right? But before we can add up all these different k things, we need to figure out what even one of them looks like. So now let's say that there's a k prime one that's like a particular one that we're interested in. And then we want to find what that derivative looks like so that we can add all of them up. Okay? So that's what we're going to have to do here.
Just give me a second.
I keep getting to the point where I said I would leave. We're not far enough. Okay, we're good? All right. So let's figure out what this derivative would look like with respect to just one k in particular. Right? So we've got the derivative of j with respect to z1 q, and we're going to say with respect to a particular k prime. So through some k prime. So this equals the derivative of j with respect to that particular p hat sub k prime, the derivative of that particular p hat sub k prime with respect to, so the h would also be, because h at this layer would be ik as well, or n by k, so the h via this particular k prime, and then the derivative of that h with respect to the qth of the z1, right? So we're gonna have to do all that just to get that guy. So what I'm actually going to do is, no, maybe I don't need to do that. and especially given the time, that would just be kind of an extra step. Okay, so we have the derivative of j with respect to a particular p hat, and that this would be -1/n times the sum as I goes from 1 to n, and as k goes from 1 to k, big K. Y sub I k, p hat sub I k, right? That's that derivative. Well, so that's just what any one of them would be. Then we have that the derivative of any given p hat with respect to h sub k is that p hat times Kronecker delta right, like that. And then our derivative of h with respect to z this time, the kth one in particular, and we've got this hk here, is actually going to be w2 qk. Okay? So let's put all these together. You just have these written down.
No, because when you're in front of the board, we can't write. I can't
Alright.
see. The denominator is q, right? The zq.
Yep.
The last one.
Alright, you guys good?
1 second. The last one is k, right?
Sub qk.
Cool.
I'm sorry, I didn't mean to put primes on all these k's. So just remember that.
Right.
Okay, so now let's put all this together. So the derivative of j with respect to z1 sub q is equal to -1/n times the sum as I goes from 1 to n, the sum as k goes from 1 to big K, y sub I k over p hat sub I k, and then times the derivative of p with respect to h, so that gives us p hat sub I k times Kronecker delta k prime minus p hat sub I k prime. And then times our last derivative here, which is z 1 sub I q.
Is this p hat I, the k is prime as well?
This one.
In the previous one, the
Uh,
denominator.
no, because we have to sum over all the k's
Oh,
that are
okay.
directly going into p. Or sorry, that are directly going into j, but then we would only take the derivative with respect to the particular one
Okay.
at the next level. Okay? So let's simplify this down. Oh, and again, sorry, I'm in a rush, so so this is in respect to a particular k, which means that we're coming through a specific k, a specific output node, right? So, simplifying this down, the z is in no way indexed by k, so we can go ahead and just pull that out. And we actually get that these guys cancel each other out, and our y distributes in. And we're going to go ahead and, to understand what happens there, we're going to break up that sum into two sums again. Okay? And then we realize that the Kronecker delta is this indicator function that is 0 for all values except where k equals k prime. And then it's equal to 1. So every term in this sum is going to be equal to 0 except the k prime term. And then we'll just get whatever y is because the delta is going to be equal to 1. Right? So then we're going to be left only with y sub I k prime in this sum. Here, we see that we have p hat sub I k prime, which is not even indexed by k, because k prime is not the index k, it's a particular one, it's a different variable. So we actually could pull that out in front, and then we're just summing over the y's. But all the y's are 0, except for one of them, which is equal to 1, so that sum also just evaluates to 1, so we're basically then multiplying p hat sub I k prime by 1. So then in that case, we get that this is equal to y sub I k prime minus p hat sub I k prime. And then we can actually distribute in the negative to then flip these around. So then this becomes p hat sub I k prime minus y sub I k prime. Okay? So this is what this looks like for just a particular, if we're coming through a particular k, right? So this is what one of the derivatives looks like that we have to sum up for our total derivative rule. But then there are k that look just like this that we have to add up. Okay?
This derivative looks like
Looks pretty familiar, doesn't it?
Mm-hmm.
No, you guys are good to move on.
Okay.
Okay? So now we can get rid of this k prime and say we now are going to be able to take this derivative of j with respect to just z1 because we know that now we just have to take the sum of the k different derivatives that look just like this. Okay? So now, in that case, our derivative of j with respect to w1 dq equals 1 over n times the sum as I goes from 1 to n, and the sum as little k goes from 1 to big K, because these are the k different ones that we have to sum up. And we get z1 iq times, now we're going to get rid of this k prime because we're going to sum over all of them. So just p hat sub ik minus y sub ik. Now we take the derivative of z with respect to h. Now what that looks like will depend network to network because it depends on what you've used as your activation function at z. But we went through all that trouble of deriving or figuring out what the derivative of the hyperbolic tangent looks like. So in this case, let's go ahead and assume that our activation function is hyperbolic tangent, and so we're going to take the derivative, or we're going to now have to multiply by that derivative. So we get 1 minus
Y squared.
z1 squared, right?
Yeah.
In this case, it's iq. Okay. And then now we take the derivative of h1 with respect to w dq, which is going to be x I d. Okay? Now there's not a whole lot of simplifying down that we can do here. We can maybe recognize that the x is in no way indexed by k, and so we can pull that out front, and some other things like that. But really, what this ends up looking like, if you guys kind of just sit and figure out what's happening with all the indexes, is that you get this vectorization. So this is the gradient with respect to W2 of J. And this is now equal to 1 over n times x transpose times oh, whoops. We left off one thing, sorry. We left off our other weight. So we have W2 in here. This is dq, and then this is multiplied by 1 minus z1 squared. Sorry about that, guys. And then this is xid. So I accidentally left that off. Because we needed to take the derivative as part of this, the derivative of h with respect to z, h2 with respect to z1. So that ends up getting stuck in there.
So that is
So let's see. Oh wait, nope, that doesn't go in here either. Sorry guys, I think I like really botched that. So yeah, so what we should have ended up with is that we, instead of with the z in there, we actually got this. I took the one derivative the wrong way. So the final derivative, the h part, so the derivative, I think I actually even wrote this down correctly, just when I went to actually do it, I like wrote it down wrong. With respect to z1, right? This is what we were trying to get to. Q, this was actually W, Q, K, right? I wrote that part down correctly, right? I did that before.
yeah.
Yeah.
We got that. Yeah.
So sorry, I got that part mixed up. So I got kind of an autopilot mode and started taking the other derivative. So because this is actually the thing that we got instead of z,
This is not the same.
then the z actually isn't in there and the w is, right? So I shouldn't have written down z, I should have written down w,
This is not the same.
right? So I apologize. So when we actually found the other derivative, it's this part right here. Okay? So it's, you don't sum over the k's, these are primed, right? There's no z, there's w instead of z, because that's how this derivative is. If we were taking this derivative with respect to w, it would have been z, but we're taking this derivative with respect to z, so it's w. So that's what I got mixed up on. And I even wrote this down correctly, but I just got in autopilot mode while I was writing the derivative down. So this is the thing that we have to sum up the k of these k different ones, and then multiply by this derivative, which gives us this, and this derivative, which gives us this. So there we go. So let's write that out a little more cleanly. So we get p hat sub ik minus y sub ik times w2 sub qk, and then times 1 minus z1 iq squared times xid. There we go. So, screwed that part up, sorry. So this now is what that derivative looks like. And then the vectorization of this gives us this here. So we can see that these all are kind of tied to the k because we're summing up over the k of these. These are not, but what this ends up giving us is So it ends up looking like this.
And the last one is W2, right?
Yep, so we have 1 over n times x transpose. And then that's being multiplied by this whole result here, which is p hat minus y, matrix multiplied with W2 transpose. And then this is element-wise multiplied with, and we say 1, and I use 1 to just kind of denote an appropriately sized matrix of all 1s, minus the matrix Z1 element-wise multiplied with itself, which is how we get all of the elements squared. So this is what that ends up looking like.
And this is just for one hidden layer.
So it gets a lot more complicated as you have to take derivatives for more and more layers back. But there's actually a pattern that I'm going to show you guys that makes it not so complicated.